Hello everyone. Yeah, I'm here today to talk about the code migration. This training and demonstration will be on the SDSC expense, but it's generally applicable to other HPC systems, and you will find similar setups in many other HPC clusters. So here's the complex slides, and this training is a part of the complex, and the complex is funded by NSF. And here's today's outline. We will first talk about the applications already available on Expanse, and then we will see whether we have any Python or R users who want to move their code to Expanse, and we will get more details about that. And the last part of the training is about installing or building your applications from the source code. We will see a few methods and to build your own applications on the HPC clusters like Expanse. Okay, first let's start to the first section, which is the applications already available on Expanse. And our staff have installed and made available a large suite of libraries and applications on Expanse. Some popular ones are such as MATLAB, QChem, or Gaussian. So you need to find a way to load them to your user environment because by default, those applications will not be loaded at your login time. So this is primarily done through the environment modules. And we also have some applications of framework like the PyTorch, TensorFlow, or AlphaFold being made available using the Singularity containers. And I will then introduce how to uh, load and start using those applications on the Expanse. And today's talk will be focused on Expanse, but what we have learned can also be applicable on other HPC clusters such as the Triton Shared Computing Cluster, TSCC, which is a campus-wide HPC cluster at UCSD, or another one is the Cosmos. And we have a few other HPC clusters here using environment modules and the Singularity containers. So why environment modules are being used for loading applications? As you may know, in a Linux system, once software or some libraries are being installed, have been installed, you will need some environmental variables to access them, such as the path where is for you to get to your application's executable. The LD library path is can help you get where to look for those shared libraries, and the C path where to look for the header and the include files. Of course, there are a few other environment variables that that can be used to access your applications or libraries. So here we under a HPC system, we will have an environment module that can load or unload other applications on demand. And the most access supercomputing side use modules, which is much more convenient than than directly setting your environment modules at runtime or in your dot .bashrc file. And here on expense and TACC and other SDSC HPC modules, we use L mode, which is Lua-based environment module system to load applications. Okay, so to use environment modules, it's quite straightforward. You need to find out which applications are already installed system-wide and become available in the module system. So to find this out, you can just run the module spider command with your the application name you want. For example, in this slide, I want to search the GCC compiler available on expense. So I just run module spider GCC. The output will list all available versions of GCC installed system widely on expense. And we can see we have GCC 7.2, 7.5, 9.2, and 10.2. And that's that if we just search the name of the application, it will show all available versions. Now, if we want to get more information about a specific version, we can run the module spider command, but with the specific versions. Like in this example, we want to know more about GCC 10.2. Then we just run module spider GCC 10.2, and the output of this command will give us two flavors of GCC 10.2. So you may want to know why we have two flavors of GCC 10.2 installed system widely. This is because those two flavors of GCC 10.2 are built on different software stacks. And if we want to get more information about one of the flavors, we just add the full name of that module key in the module spider command, and the output will show that this specific flavor is built on a software stack called GCC 0.17.3b. And on expense, we have CPU and GPU software stacks. The module stacks are different for the CPU and the GPU applications. So each CPU and GPU stack has two versions, which is point 0.15 and 0.17. And we cannot just mix the two stacks as something compiled for the GPU stack will not work on the CPU nodes, and vice versa. So if you want to use GPU nodes, you should load your applications from the GPU software stack. And if you want to use CPU nodes, of course, you should use a CPU software stack. And we also have a few application examples provided in our public storage area, which is CM shared examples SDSC, for you to see how to run those applications, including how to load those load modules for accessing those applications. Okay, so once we know the exact modules we want to load, we can just run the module load command to load those modules. If we want to load a specific version of that module, we can just add the version at the end of the application name, so that version of the application will be loaded. To unload a module, we can just run the module unload command. If we want to list all the modules currently loaded in our user environment, we can just run the module list. It will return all the modules currently loaded. To reinsert our modules in our user environment, we can run the module reset command. Then the modules will be reset to the default. If we want to clean everything in our user environment, every modules in our user environment, we can just run the module purge command. So what does the module change to our user environment exactly? To know this, we can just run the module show command to display the details of all changes that will be made in our user environment. For example, if we run the module show CPU 0.17, then the output will tell us what these modules for, and any environment variables have been changed if we loaded this CPU module. And of course, the module command can be added to your .bashrc file to make it run automatically at your loading time. And you can even create your own module file to load your own applications uh, or libraries. But I will not cover this in detail today, and I put this this detail at the end of this slides, and you can take a look if you need. And now here is a short summary of the useful module commands. We first learn how to search a certain application module with the module spider command, and then once we get the module name we need, we can just run the module load or to load that module or unload that module if we don't need it. And the module list command will list all currently loaded modules. And if you wish to reset the module, you can run the module reset command, or similar to purge all the modules in your user environment. And the last, if we want to know what kind of changes have been made after loading a module, we can run the module show command to get the details. Okay, any questions so far about how to run modules?
No questions at this time, Yuwu.
Okay, so I will go ahead, and here is a hands-on session, and I will show this command on expense after my lecture. And if you are interested, you can practice by yourself as the homework. Okay, besides the environment module, we also uh, use Singularity to install some applications system-wide and make them available. So because those applications are easier to make available by the Singularity container. On the own expense, the containers can be found on at two paths. One is CM shared and another is expense projects. And those applications I mentioned uh, uh, so- for example, the TensorFlow, PyTorch, AlphaFold, ParaView, VZ. uh, And we also have the E4S available one by a container. Besides the Singularity container, we also have a few Singularity definition files available for users who wish to add to the containers or wish if they want to rebuild the Singularity container or update or make any modifications of the applications or libraries in the container. And we put those definition files in a GitHub repo. And if are interested in why is Singularity so popular on HPC, I put those slides at the end, but I will not cover it today. Okay, so to use applications via the Singularity containers, all you need to do is start a Slurm batch job or a Slurm interactive session, and then load the Singularity modules to make Singularity available to you, and then you can start run Singularity containers. In this example, it's a batch job script. The first part of this job script is nothing but a few SBatch command lines defining how much computational resources you want for your job. And we have specified, for example, the GPUs, the what time of the job, the job name, and where the output file should be saved. And then the second part highlighted in red is about how to load the Singularity module. We just reset our module environment and then load the Singularity module called Singularity Pro. Then the Singularity executable will become available. And the last part is about the exact Singularity command we are running in this example. And in this example, we add a bind path and specifying where our Singularity command containers is saved, and how to run the executable inside the Singularity container as highlighted in this example in blue. The executable we want to run is Python 3, and the last part of this command is about a Python script. And if you want to build your own containers, that's also possible, but it's also conditional. When there are lots of dependencies that cannot be installed easily in the regular expensive environment, you may want to explore the possibility of putting all of them into a Singularity container, or if you already have one, but you want to update that container, then you can build your own Singularity container with the Singularity build command. But on expense, running Singularity build can only create a simple Singularity image. So back to our Singularity containers building. So we can run the Singularity build command to create our own Singularity images from other images only. So for example, this I'm building a new container from the dot hub, and that's possible on expense. If your containers have NPI, then you need to make sure your NPI matches the external NPI version on expense, and make sure the InfiniBand drivers are installed in the container. If you want to build a GPU containers, then you need to make sure the packages installed are compatible with the driver on our system. I would recommend you to build the GPU Singularity driver containers from the NVIDIA GPU cloud. They have a huge amount of the the containers available already, and what you need to do is just run the Singularity build command to get to build your Singularity images from them. And as I mentioned a few slides earlier, the Singularity we already have a few Singularity definition files for users who wish to update their containers or rebuild them on expense. It's saved in this GitHub repo. But builds from definition files need root access, so it cannot be done on expense. That means you need to build it elsewhere with those definition files. For example, use your laptop, desktop, or on cloud-based cloud resources. And here is an example of the Singularity definition file, but I will not cover the details of the file in today's training. We have more Singularity training at SDSC. For example, we will have one more training about the containers on June 11th. And if you are interested to learn more about Singularity, you're welcome to register and attend that training. And if you want to learn more right now, so we also have a few past trainings recorded, and I also put those links in these slides. Okay, here's the short summary of the Singularity containers on expense. First, we already have many applications available via the Singularity containers, and they are saved in some public storage area. And we also have some Singularity definition files available for you to modify or rebuild the Singularity containers if you need. And I also introduced how to build the Singularity containers with the Singularity build command, but that command can only run on expense when creating the Singularity images from other images on some repositories like the dot hub if you want to build from a Singularity definition file, your laptop or desktop or some cloud resources is required for you to have the root access. And if you want to run MPI or GPU inside a container on Expanse, you need to choose the compatible MPI or GPU packages when building your Singularity containers. And here's the hands-on session 2, working with Singularity containers, and I will also show this uh, in our QA session, before our QA session, after my lecture. And if you want to practice by yourself, uh, please try it. And I actually already put the code for these hands sessions in a GitHub repo, which is under the SDSC complex. So if you wish to try those code, you can just go to that GitHub repo to grab the code. Okay, any questions so far about the Singularity containers on Expanse, or any general questions?
Nothing in the chat right now, Yuwu.
Oh, okay, no problem. And feel free to ask the questions during my lecture or in the Q&A sessions, and then I will move to the next two sessions, which is about the Python and R-based applications and the libraries available on Expanse. Uh, I will mainly focus on the Python one because I don't expect to there are any R users today. But if you are running R very often, please let me know. So I will introduce more about R. So the Python applications and the libraries are also available via the environment modules. We already installed those applications and the libraries system-wide, and made the modules available to our Expanse users. And those modules begins with the py, so which is for Python. So to uh, to get which Python applications and the libraries are installed system-wide, you can run the module spide py dash command, and then once loaded, you can run the module shell command to get more information about the Python libraries. And some of these modules are dependent on MPI, like the MPI for Py, CF. But you need to pay attention to the patch version available by the modules, because some of the modules installed system-wide may be a few years old already. Maybe they are out of date, so cannot meet your requirement. So just pay attention to the patched version available by the modules. If you need other Python libraries or applications, so it's best to go to the conda or Singularity approach. That's what I'm going to introduce after the Python modules. But please do not mix the Python applications and the libraries from the modules with one from conda or a container. they will likely conflict or even feel you're wrong. And I know some of our Python users are running MPI related code with the MPI for Pi. So I am listing all of the MPI for Pi versions and the flavors in this table to show how many versions of and flavors of MPI for Pi are available on expense. But note that if you do a conda install of MPI 4Pi instead of loading the modules, it will use the conda-based MPI install. This is okay for single node cases, but if you want to scale your run to multiple nodes, you will need to compile your MPI for Pi from the source code instead of using the conda based MPI. Okay, so to uh to get your own Python applications or libraries, you can install a mini forge uh, to use conda or member to install those packages you need. And even if you are Jupyter notebook or Jupyter Lab users, you to build your own conda environment, you still need a mini forge or similar tools to set up your conda environment. So that's why we recommend you install your mini forge first. We we are introduced Mini Forge 3 rather than Anaconda 3 or Mini Conda 3 because Mini Forge 3 is replacing those two the recent years because Mini Forge 3 already includes the member by default and will use member to install Python packages by default. Uh, and the member install is much faster and easier to troubleshoot than the conda install. Okay, here this slide introduces how to install Minifold 3 on expense. Please remember to start an interactive session on a compute or GPU node on expense before you install, and then you can start download the installer script with the wget command, wget command, and then you can begin to install the Minifold 3 and create uh, allies to load it when needed when needed at runtime. And I also list all conda or member commands that are useful when running or installing Python libraries and applications on expense, for example, the member info command can show the current member environment info, and the member list can list the list patch details in the current environment by line, and a few others you, you may need when building your conda environment or installing any Python applications or libraries. But by default, you still use even you have the member available, you will still need to use the conda activate or deactivate your conda environment because that only that conda hood will be enabled after you load the Mini 43. And here are a few other notice about the conda or member install. You should keep in mind that your base environment should be small or even untouched because if you get a large base environment by adding additional Python packages into your base environment, uh, conda or member installation will become slow or even fail. Generally, please let only conda and member live in your base environment. And on any HPC environment, please install conda environment in your home directory. You cannot run conda or member installs into any larger locations, which is your scratch directory. That can cause system-wide problems due to metadata loss. If you want to install some libraries related to GPU, please make sure the packages chosen work with driver on expense. For example, the current driver versions on expense can only support CUDA 12.0, so make sure any CUDA-based installs are with a CUDA version that is 12.0 or older. So that can make sure the Python packages you installed are compatible with our GPU driver on expense. And here I also want to introduce UV to replace pip or virtual when installing Python packages. UV is a single tool to replace the pip, people tools, PeopleX, and I mean many other many other pip installation tools listed here. This is because UV runs much faster than pip, and with a universal log file, it can manage different projects in various Python versions. That's very specific for your Python projects. So that means you can start different Python versions and build Python libraries on based on that particular version for each of your projects. But UV is not a replacement of the conda environment. You can still install UV into a new conda environment and run UV to install Python packages inside a conda environment, or you can just install UV into your base environment. The change of your base environment is minimal, so your conda or member will not be affected. Okay, next part is about the R-based applications. I will make it really pretty if no more R users here. And similarly, R applications and packages are already available in environment modules as we already installed them system widely. We can run the module spider command to search or install R applications and libraries. And also we need to pay attention about the package version available in the modules. If we need to install more R applications or packages, we can choose to install them from source, conda, or the Singularity. So the next few slides are for the R users, like how to install R packages from source, and why we should choose the R package installations from source over the conda install. And sometimes we can choose install those packages inside the Singularity. And last part of this session is about an example of using R by the Singularity. And for those R users, we already have more training for about running R on this HPC environment. Okay, here is the short summary of Python and R-based applications. The Python packages are available via the modules, but you should check the versions before use. And you can run conda or member install to install your own Python packages, and to make conda or member available, you should install Miniforge 3 first in your own space. Sometimes you can build those Python packages inside a Singularity container to build an isolated environment with the Singularity. And also we have R-based applications and packages available via the modules from source or conda member install or inside the Singularity container. And here's another session, hands-on session. I can demo in later after the lecture. And the last session of today's training is about installing or building the applications from the source code. And we can sometimes choose to install our applications from the source with or compilers and the libraries and the dependencies of already available on Expanse. And those applications usually have the config scripts that can pick up the dependencies based on the current user environment variables and options. And we provide an example of building application from source, which is about the building content espresso, and we have a job script for that building saved in our same shared area. To before the configuration, we can also consider loading a few dependencies via the environment modules. Like in this example, we build before we build anything, we load those modules. So those modules, the applications from those modules can be available at the compiling time. And we can also specify a few compiler flags. For example, here to build the content espresso, we specify which CC or Fortune C or Fortune compilers to be used, and what C flags or C plus plus flags or the Fortune flags we want to use. And of course, we can also set up a few environment variables directly before we configure and compiling the source code. And I also want to add a note about the installation location. Here I highlighted the installation location in red here. In many applications configuration step, you can specify where the applications to be installed. Here I by the prefix option. Here we need to specify the installation path to our own space. Uh, for example, here is a subdirectory under our home directory. Otherwise, many applications will choose to install the software into some system path that you cannot do it without root. And after the configuration step, we can just compile the code with the make command and the make install to install the applications. And sometimes the applications just provide us with a make file, so we can update that make file to specify the flags, the installation locations, and the environment variable inside that make file, and then we can just run the make command to compile the code. And here a few notes about installation from the source. All GPU compiles must be done on a GPU node on expense, and also don't mix installs from GPU and CPU stack. If you choose to compile the code on the loading node, it will fail on a GPU node. But if you have a CPU code, that might be okay to compile on the loading nodes, because the CPU processes can match on expense. If your applications needs a BLAS or LAPACK or scale LAPACK, we also have a few options on expense. So you can build those libraries from different from one of the resources I listed here. For example, for OpenBLAS, the MKL, and those again, those libraries will be installed in standard locations, can be configured by some options specified in your config command or in the make file. So you can point the build scripts to get to the right locations. And on expense, almost all of our nodes have the AMD CPUs, but we also have Intel compilers. Intel compilers can work fine on those AMD nodes, but just change a few flags in the configuration step, so to make the Intel compilers work on the AMD nodes. And nowadays, we also use spec to install applications from source. For example, the CPU and the GPU software stacks I mentioned earlier in the module environment section. It's built by or built by spec. We use spec to build our module our software stacks and create those modules. But as a user, you can also use a spec to build your applications from source, and we have we have a GitHub repo, which is github.com/SDSC/spec to save those scripts and the spec package repos for some machine specific installs. And also AMD provides some spec recipes and specifications uh, on their website. So if you're interested in installing from source with spec, you can take a look of the link I provided here. And here is the last hands-on session I have, which is about building applications from the source on expense. And here is the take-home message. Before we go to the demo session and the Q&A. First, we have learned all the applications are already available on Expense, and of course those environment modules and the Singularity containers might also be available on other HPC systems. You can check if the applications are already installed via the module on or Singularity, and then load those modules to get those applications you need. And then we learn how to build the Singularity containers with the Singularity build command and a few restrictions like if you wish to use the definition files to update or rebuild containers, you need a root access. So you need to build those new containers on your laptop or some cloud-based platform that you have root access. And in the next two sessions, we learn how about something about the Python and R based applications and libraries on Expense, and they can be loaded by the modules, and they can be built by the conda or member from the Mini 43, and of course they can also from the Singularity containers. And the last session is about the installing or building applications from the source code. And just pay attention that we cannot install those applications into a system path. So you need to specify the installation path to your own space, like in your someplace in your home directory. So thank you. That's all about my lecture. And next, I will go to the expense. Let me let me log to expense first. Sorry, I lost my I lost my connection a while ago, so I think those expense session are also being lost. So while I'm logging to the expense, any questions or comments so far?
Yeah, there's one in the chat. For a Python/C++ research workflow that uses MPI, OpenMP, CUDA, and PyTorch, what is your recommended decision process for choosing between environment modules, Mini Forge/Conda, Singularity containers, or spec?
Okay, that's good questions. Generally, I would if if just for the PyTorch or a few libraries built on the PyTorch, I think installing with the mini with the conda or member with from the Mini 43 should be sufficient. and easier to use. So that means you don't have to learn more about the Singularity or Spec. So if you're already a Python user, you probably already know how to run the conda or member install, right? So that's my recommendation. But if your Python packages are too complicated to build with the member install, then I would suggest you go to the Singularity or Spec route. So we it's likely that we already have a few recipes for building those Python packages via the Singularity or Spec. And that's so that's my recommendation. And now I have logged into to expense. So let me uh let me show a few commands on expense that that can help you better understand what we have learned today. So first session is about working with modules. So in a hands-on session, we are asked to find out all the available MATLAB modules. So to do that, we can just run module spider MATLAB. It, it's not case sensitive, so you can just use all lowercase. And here the output, now according to the output, we say we can say that there are three versions of MATLAB available, and what system wide. And if we want to get the last one, 2022B, we can then run the modules by MATLAB 2022B again. So the output will show two flavors of this version. So we can choose the one about the GPU built on the GPU stack. We can then just run the module spider again to make sure we are loading the correct MATLAB versions. And if we choose the first flavor, we'll see that it's built on a CPU software stack. So instead, we check the second one. That one is built on the GPU software stack. So we can module reset to make sure we change back our module environment to the default, and the default is loading a CPU software stack. So to change that, we can just run MATLAB module load GPU MATLAB 2022B, and then we can run module list again to get our modules currently loaded. So as you can see that we are now loading a GPU software stack as well as that 2022B MATLAB built on that GPU stack. And we can also run the module show command to show what exactly changes we have after load if we load that MATLAB modules. You can see a lot of introduction part, and the path has been will be changed by adding the path to the MATLAB executable after we load that MATLAB. And of course, you can also run which MATLAB command to confirm that the MATLAB executable is from the GPU stack. And the next hands-on in the next hands-on session, I have a few comments about an example of working with the Singularity containers. So in that example, we can just call let me we can just copy the example from the same shared examples SDSC PyTorch to our current directory. Yeah, remember already have a lot of examples available for you to run those applications on Expanse. So if you're not sure how to start, maybe you can just go to that example location to see if there are examples available. So I already copied the PyTorch into my Scratch directory. So I will skip the copy command, but just go to the PyTorch. And here, then we can start we can start a job. We can start an interactive job with the job script available here. For example, if we open the jobs example, you can see what resources we have and what kind of modules are loaded in order to use Singularity. And the last part is about how to run the Singularity command. And in the second part of this hands-on session, I show the example how to build a Singularity image on Expanse, which I already did, and I saved that image into my home directory part. Remember, running Singularity containers takes resources too. So we should put the Singularity run command into a job script or in a interactive session. Like what I'm doing is I'm trying to start an interactive job with the srun command, and once I get the interactive session, I will be assigned to one of the expense nodes. And here you see that the host name before my prompt has become from the login to exp, which is expense -1-19. That is one of the compute nodes on Expanse. So then I can load uh, the Singularity module, which is Singularity Pro. Module load Singularity Pro, and I can then run the Singularity build command to build a image directly from the Docker. But I think I already built that, and then I can just run the Singularity execute command to run that image. And that image has a few executable put inside the container. For example, the fortune command. Oh, singularity. And the fortune executable will return some words. And or the cow say hello inside the example, and the output will show a cow saying hello to us. And we can combine both the fortune and the cow say into one bash shell. Fortune and the cow say. So the cow can say something from the fortune like this. I think I make it right. Oh, okay. I should be the single chord. Okay, so now the cow is saying something from the fortune. In our next session is about working with Python or R, and still installing or running Python or R code should be in a interactive session or in a backdrop. And I already included installed my mini forge and set a Linux alias to load mini forge. So after running mini forge, I can I can then load the mini forge tree and get to the base environment. And I think I already have the conda environment called PyJoes, and just use the conda activate PyJoes to active that conda environment, and then we can try some PyJoes. I think that's the that's the way to 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 uh, to to load those Python packages. And I will skip the R session because no one here is running R. And the last session is hands-on session is about the installation from the source code. And still we should run this inside an interactive session. And here in my example I I'm installing an application called C matrix from the source. So to get that to install that C matrix, I can search the source code online, like for example in Google say C matrix, and download the source code from the GitHub repo, and then change to there, and be, to configure and comply. And of course this one is special because I need to load a few additional modules, like about the N curses. And then I can begin to build build the C matrix with and this one comes with the auto reconfigurations. So once uh, I run the auto reconfig, a config file can will be created. Configure command will be created, and then I can just config the we to and specify where to install matrix and specify the labs uh, to the anchors. Okay, cannot create executables. What's my current? Oh, I'm still have the mini forge 3 loaded, so that's why I'm mixing my GCC environment. So uh let's see, let me deactivate and SW. I think I am getting the library name correct now. Okay. And after make make install, okay, that's fine. The permission denied message will can be ignored. Okay, after the installation, I will find my C matrix executable under the path I specified. And what I need to do is I can just run this executable directly, or add its path to the path environment variable. To And now if we run which C matrix, it, let me see if this is good. Okay, now it's good. And the last step is verify my whole installation by running that executable. So that's how it looks like. Okay, that's all of my demonstration today. Any other questions, comments about today's training?